Hey, what's up, everybody? This week we're going to be learning about servos. Typically, throughout the year, at this point, or maybe even a little sooner than this point, we would have been moving into controlling the little desktop robots. And in order to do that, we would be using servos. So, if anybody here is familiar with like RC vehicles, cars in particular, they use servos to like control the direction of the wheels. RC boats use servos to control like the direction of the rudder. RC planes, if you've taken principles of engineering and made your model airplane, you've used servos there as well. So um, this week we're going to be talking about that. And we're going to do a couple activities moving forward with some servos. So let's continue on. So what is a servo? A servo is a small DC motor, but unlike most DC motors that are just simply a motor, um, a servo has an integrated circuit built right into it, and it has three wires that go into it. One of the wires is a ground wire, one of the wires is a power wire. Servos typically get powered off of 5 volts, and then one of the wires is a signal wire. So unlike a regular DC motor where we just like send power to it and it turns on, servo actually has integrated circuits within to be able to control that servo, the position, the speed, the rotation, all sorts of different things. Okay. Um, there's also a gear train built in there, okay, like its own gearbox to make it a lot more powerful. Servos, for their size, are really powerful. Again, they have their integrated circuit so that they know things like position, speed, location. They also know things like position and speed because they have a built-in potentiometer. They have an output shaft, but that potentiometer will measure the output shaft and provides feedback for closed loop control to the integrated circuit so that it knows where it is. There are two different types of servos. Typically, we deal with both of these in class. A standard servo, which is a servo that is used mostly in RC and other sort of like controls. They only have a limited range of motion, but we can be very specific with what angle they're set at. And then there's also continuous rotation servos, which we use typically to control the wheels on the robots. They turn continuously, as the name suggests, but unlike a standard servo, you can't specifically determine what position they're at, but you're able to either turn it clockwise or counterclockwise, and you can control the speed of that. So again, to go over some of the differences here between the two of them, a standard servo can only rotate between 0 and 180 degrees. The speed of that servo is controlled by the integrated circuit. We can't make it go any faster or slower. It just goes to its position based upon the circuit. Um, and you can send the servo a specific position, and it utilizes its internal pot to get its internal potentiometer to get to that position. A continuous servo can rotate continuously instead of just rotating a specific amount. We can vary the speed of those servos by changing the values that we apply to it, but we cannot control the specific position of the servo as accurately as we could a standard servo. We also can control the direction that it turns, either clockwise or counterclockwise. And that's true actually for both servos. So when we write a program that uses servos, we need to include the servo library. Okay, this should be your first line of code after any initial comments made. And when you go to put this in, you're going to do a pound sign or a hashtag include, and then within carets, you're going to write capital S servo.h and then another bracket. There's also an option within Tinkercad or Arduino for that matter, where you can load the servo library. And I'll show you how to do that once we get into Tinkercad. But you could also simply just type this at the top, and that would include the servo library. And the servo library has a whole bunch of like all of the controls necessary to make servos work. Um, in most programs, to this point, we've declared like hardware using constant integers, okay? Like an LED, we can say like a constant integer LED is set to pin 13, for instance, okay? But servos are set up differently than that. Because Servo is its own library, they've set this up based upon the library. And Servo is its own data type, just like an integer or just like a long. Um, but unlike anything else that we've done, we're not going to declare the pin after it. Okay, so if I want to create a servo, um, I'm going to first type servo, and this would be typed in like above your void setup. I'll show you that in a little bit. And then you're going to name your servo. Okay, so in my case here, the servo is named left servo. I could also name it like right servo. I could name it Bob if I so desired. What I can't name it is servo by itself, okay, because that is a data type. So you're going to create and declare your servos using the servo data type. In order to determine what pin our servo is attached to, we need to use the attach command, okay, or the attach function. So the attach function will assign the servo to a digital pin. So if we were to look at an example here, we have the first line of code is we're including our servo library, okay, include servo.h. Notice that there's no semicolon at the end of that line of code. Then the next line, we are declaring the name of our servo. So in this case, servo is named left servo. And then within our void setup, we're going to say left servo, which is the name of our servo, dot attach, which is we're trying to connect it to a specific pin. And then within the commas, or I'm sorry, the parentheses, we're going to include the pin that the servo is attached to. So actually, let's go through that real quick before we start talking about the rest here. So we're going to come back to circuits here, and I've created a standard servo activity. Going back to servos actually for a second here. Typically in class, we deal with both a standard servo and a continuous servo. It seems that there is no such thing as a continuous servo in the Tinkercad ecosystem. So we're only going to be dealing with standard servo activities this year, unfortunately, just due to the limitations of the software itself. So when I come over here, I have my standard servo activity. And the first thing I need to do is bring in an Arduino. And then the second thing I'm going to do is bring in a servo. Okay, there's two different types of servos here. You can choose either of them. It doesn't really matter. So first thing we're going to do here is start to wire this up. So we have our power connection, which we're going to bring to 5 volts. We have our ground connection, which we're going to bring to ground. And we have our signal connection, which we can bring to like any of our digital pins. I'll connect it up to pin 7 for right now. Okay, set my colors so that everything seems to make a little bit more sense. And then we can begin by just declaring this servo. So we're going to run into our code here. And we're going to go to text. And we're going to get rid of the stuff that's in our void setup and in our void loop. So first thing we need to do is add our name. Okay, then the next thing we're going to do is include our library. So notice this button that I've selected up here. This is the libraries pad. And if we run down here, we can select the servo. So I'm going to say include. And notice that at this point now, it's included that # include, and then in brackets, servo.h. Let's put it at the top line. That's perfectly fine. You don't need to move it. The other thing that you could do once again is you could simply just say include servo.h here, okay? And then again, we're going to name our servo. So when we name our servo, we're going to do that above void setup, and I'm just going to call this example. Okay, and I'm going to put a semicolon there. So when we come to our void setup here, we're going to say servo capital S dot attach. Actually, maybe that's incorrect. Hold on one. Yeah, sorry about that. So going back to the notes here, I need to put the name first, dot attach. Okay, so when we come back here, instead of just saying servo, we're going to say example at this point, dot attach. And then because my servo is connected to pin 7, I'm going to put pin 7 in there like that. Okay, so if I were to start my simulation now, this comes up. I don't know why. Let's see here. Let's just go back to actually adding it the right way. Oh, because I forgot to put a capital S there. Okay. All right. That's my bad, Tim. Let's see here. So let's just fix that. Capital S. Now I start my simulation. Okay. Maybe it doesn't want us to be able to include it ourselves. So let's just go through the process of using the library that they assigned to us. Now let's try starting our simulation. Okay, so at this point now, it is running. Servo is working here, so we can start to tweak some of this stuff from here. So let's go back to the notes and we will continue on. So we've attached our servo. So we're going to use what's called the right function to tell the servo what direction we want it to turn and how far. Servos are controlled with PWM signals, okay, that are called signal trains. Unlike other PWM signals, we don't need to actually connect this to a PWM ports. We can connect this to any because of the servo library itself. And unlike other signal trains, this is going to be dealing with microseconds, which is 1/1,000,000th of a second. So it's a really like high on and off signal train that gets sent out. The high signals instructions for the servo's integrated chip, and that's the thing that's going to control the direction and the speed of the servo. And the great thing about the servo library is a lot of this is done in the background. So when we want to move our servo, again, our servo goes from 0 to 180 degrees. We're going to use the right function. So the first thing we're going to do is include the name of the servo. So again, in my example here, the servo is named example dot right, and then within parentheses, you're going to put the degree number that you want to move it to. Now, because this is an actual physical device and it takes time for that thing to move from one position to the next, you have to delay to the next line of code before you can finish the code up. So you need to delay like probably a minimum of a second. The further the system needs to move, the longer it's going to take for it to get there. So for instance, the servo can go from 0 to 90 degrees in half the time that it takes for it to go from 0 to 180 degrees. All right, so depending on how far the movement is, you might have to increase the length of the delay, because if you don't and you move on to the next line of code, it'll just stop wherever it ended and then move on to the next line of code. Okay, so we need to delay. Detaching is what happens when we pull the servo off. And if we were dealing with these servos in real life, detaching is really important because servos are not perfect at holding their position. And typically, like what will happen is the servo will make all these micro adjustments as it gets to where it's supposed to be. And if we were running a servo off of, let's say, a battery, all those micro adjustments are going to kill the battery. So we can detach our servo really easily by just using the name of the servo dot detach. and that'll stop it from trying to hold its position, and instead it will just stop it exactly where it was, i.e. holding its position. So an example code here would be, again, include servo.h, servo, name of our servo, in this case, servo left. And then within our void setup, we're going to have servo left.attach 13. So we've connected the servo to pin 13. We can say servo left.write 90. That's going to move our servo to the middle position. And that could be it. Okay, that would just go from where it was to 90 degrees, and it would stop. We could also detach that later on, and we're going to work our way through this here. So this week, your goal is to write a program that the servo is going to start at 0 degrees and wait a second. Then it's going to go to 45 degrees, wait 2 seconds, 90 degrees, wait 1 second, 45 degrees, wait 2 seconds, and then 170 degrees. You're going to need to wait some time for it to get there, and then you're going to detach. Okay, so that's going to be the activity that we're working on this week, and I'll show you guys like a little bit more of how that works over here. So at this point, we have our servo named. We've included our servo library. We've attached our servo to pin 7. So let's try moving example.write, and let's go to, like, say, 45 degrees. So if I start my simulation, you'll notice that my servo has now twisted. That's excellent. Now, watch what happens here. Let's say that we go from example .write, and let's go back to 0 degrees. Actually, no, let's go to, 0 degrees. Watch what happens to the servo right now. Notice how the servo really hasn't moved. It's only moved to 0 degrees. That's because it went through the code to 45, but there's no delay afterwards, and it went right back to 0. So watch what happens when I add a delay in here of 1,000, let's say 1,000. Let's start our simulation. Now we're going to see it move, and then we're going to see it move back again. Okay, and if I wanted to, let's say now go to like 150 degrees, I could then delay like another second. And we can see that. And again, I forgot to put the delay here, so I need to include that because it didn't go back to 0. So we're going to say delay 1,000. Then it goes back to 0. Now it's going to go to 170 degrees. Okay, so at this point too, we can detach if we want to, right? So in order to detach, all we have to do is say this is our example dot detach, close our brackets. You don't need any sort of number here because example is already attached to pin 7. It's going to know to detach it from pin 7 as well. So you're just going to leave these open. So we're going to go into here, into there, to there again, and then back. Okay, so again, this is an example code, but you need to make your code run like this. So you're going to start at 0 degrees, wait a second, go to 45 degrees, wait 2 seconds, go to 90 degrees, wait 1 second, 45 degrees, wait 2 seconds, and then 170 degrees, wait some time, maybe like a second or two, and then you're going to detach. Okay, so that's the activity for this week. If you guys have any questions, you can give me an email, and I'll talk to you all soon. All right, bye-bye.